Imagine being able to identify unknown substances by simply shining a special kind of light on them. That's the power of FTIR spectroscopy. FTIR stands for Fourier Transform Infrared Spectroscopy. It's a powerful technique used to identify organic, polymeric, and in some cases, inorganic materials. FTIR spectroscopy has revolutionized various fields from chemistry and pharmaceuticals to environmental science and art conservation. FTIR spectroscopy relies on the interaction between infrared or IR radiation and the molecules of a substance. When a beam of IR light passes through a sample, the molecules absorb specific frequencies of the light, depending on their chemical bonds. This absorption pattern creates a unique fingerprint for each substance, allowing us to identify it. Think of it like a fingerprint scanner that uses light instead of your finger. Just like every person has a unique fingerprint, every molecule has a distinctive way of absorbing IR light. This allows scientists and researchers to identify unknown substances and analyze their chemical composition. FTIR spectroscopy offers a rapid, non-destructive method for material identification and analysis. Its versatility and wide range of applications make it an indispensable tool in numerous fields. Whether it's developing new drugs, monitoring air quality, or authenticating artwork, FTIR spectroscopy plays a crucial role in advancing our understanding of the world around us. The basic principle behind FTIR spectroscopy lies in the way molecules vibrate. Every molecule has a unique set of vibrational modes, which are like tiny dances performed by the atoms within the molecule. These vibrations occur at specific frequencies within the infrared region of the electromagnetic spectrum. When infrared radiation is passed through a sample, the molecules absorb energy from the radiation, and their vibrations increase. However, only the frequencies of IR radiation that match the vibrational frequencies of the molecule will be absorbed. This absorption of energy at specific frequencies results in a spectrum. This unique pattern of absorption and transmission creates what we call an infrared spectrum, which acts like a molecular fingerprint. By analyzing the peaks and valleys in this spectrum, we can identify the functional groups present in the molecule and ultimately determine the identity of the unknown substance. FTIR spectroscopy relies on a mathematical operation called the Fourier Transform. This mathematical transformation converts the signal from the time domain to the frequency domain, allowing us to see the individual frequencies of light absorbed by the sample. This transformation is essential for interpreting the complex data obtained from an FTIR spectrometer. An FTIR spectrometer is a sophisticated instrument that measures the absorption and transmission of infrared light through a sample. It consists of several key components working together to generate an infrared spectrum. The main components of an FTIR spectrometer include 1. The infrared source. This component emits a broad range of infrared radiation. 2. The interferometer. This is the heart of the FTIR spectrometer. It uses a beam splitter to split the IR beam into two beams, one of which passes through the sample while the other acts as a reference beam. The two beams are then recombined, creating an interference pattern. 3. The sample holder. This holds the sample being analyzed and allows the IR beam to pass through it. 4. The detector. This component measures the intensity of the IR radiation that passes through the sample. 5. The computer. This component controls the instrument, processes the data, and displays the resulting spectrum. Here's how an FTIR spectrometer works. The IR source emits a beam of infrared radiation, which is then directed into the interferometer. The interferometer splits the beam into two and introduces a controlled path difference between them. When the two beams are recombined, they interfere with each other, creating an interference pattern called an interferogram. This interferogram is then directed through the sample, where absorption of specific frequencies occurs. The detector measures the intensity of the transmitted light, and the computer uses Fourier transform to convert the interferogram into a spectrum. FTIR spectroscopy has become an indispensable tool in countless fields due to its ability to provide detailed information about the molecular composition of materials. Let's explore some of its remarkable applications. 1. In the pharmaceutical industry, FTIR spectroscopy is widely used in drug development and quality control. It helps identify and quantify pharmaceutical ingredients, ensuring the purity and consistency of medications. 2. In environmental science, environmental scientists rely on FTIR spectroscopy to monitor air and water quality. It helps identify pollutants, greenhouse gases, and other contaminants, enabling effective environmental monitoring and remediation efforts. 3. In forensic science, FTIR spectroscopy plays a crucial role in forensic investigations. It assists in analyzing evidence such as fibers, paints, and polymers, aiding in criminal investigations. 4. In food science and agriculture, FTIR spectroscopy helps ensure food safety and quality by detecting adulterants, identifying the origin of food products, and analyzing the composition of crops and soil. FTIR spectroscopy has revolutionized scientific research and industrial processes by providing a rapid, non-destructive, and highly accurate method for material analysis. Its versatility and wide range of applications have made it an essential tool in advancing our understanding of chemistry, biology, materials, science, and many other fields. As technology continues to evolve, FTIR spectroscopy is poised to play an even more significant role in shaping our world.